So it's time for another circular motion example, and this one will also involve some magnetism that we've covered a while ago. So let's check it out. A proton moves along a circular path in a region of a uniform magnetic field. The magnetic field is directed into the plane of the page, as we can see here by the representation that we've learned in class, right? X's, they mean into the page, and dots with a circle around them means out from the page. You may view this as if it was an arrow, right? Very old-fashioned arrow. Alright, so label with arrows on the diagram the magnetic force F on the proton. So as we remember, we should apply our right-hand rule, right? So how does that work? Well, this is my index finger, this is my middle finger, and this is my thumb. Oops, that's awful. This is my thumb. And the other fingers, they are closed. So basically, this is going to represent the velocity of your vector, of your particle. This will represent the field, the magnetic field, and your thumb will represent the direction of the force. You can see that all three of them, they are perpendicular to each other, right? So that's very important. Now, so let's see. If this proton, this is a proton, so everything here holds. If this was an electron, our velocity would be opposite, or the force would be opposite. Okay, so since our field is going inside, if we put our hand here on top, we would see that, well, the force has to be going in that way, right? And velocity would be going that way. So we have labeled our magnetic force, and if you observe this, it matches with your right-hand rule. Now what about for B? Label with arrows the velocity vector. We've done it, right? 90 degrees, it's tangent to our circular path. Now for C, the speed of the proton is 2.16 times 10 to the power 6 meters per second, and the magnetic field strength is 0.042 Tesla. For this proton, determine in meters the radius of the circular path. Give your answers to an appropriate number of significant figures. Alright, so how is this going to work? Well, first we can calculate our magnetic field, our magnetic force. And our magnetic force, since everything here is 90 degrees, right? Because if you look at your booklet, you would have QVB sine of the angle between velocity and the field, but since they are perpendicular to each other, there's going to be 1. So QVB. Also, I will have my centripetal force, and my centripetal force is mv squared over r. There are other ways of representing the centripetal acceleration, but all of them basically use v equals omega r. So if you remember this and this, you can get to any of the equations that you need. Now, since the magnetic force is the one which is holding the particle, it is the centripetal force. So we can basically make them the same. So QVB is equal to mv squared over r. Now we are looking for the radius of the circular path. So let's make r our subject. Before we do that, we can cross out the squares. And now let's make r our subject. So we get r to here, and that's mv over qb. If we take the numbers, so 2.16, that's the speed of the proton, that's our velocity here. The mass, you can see in your booklet, you can check in your booklet. The magnetic field strength 0.042, and Q, which is the charge of an electron, which you can always see in your booklet. Just so you have the numbers, the mass here would be approximately 1.73 times 10 to the negative 27, and our charge 1.60 times 10 to the negative 19. And if you're using SI units, that would give you the radius in meters. And then we'll have, if you put the numbers in, approximately 0.538 meters. But that's a bit too many significant figures, since this is only two significant figures. we would instead represent this number as 0.54 meters, rounding this up.